Hello, hello. Today we're going to talk about the Zane. If you watch the Hotel Transylvania, the Zane is a moment of love at first sight. Just look at this GIF here. If you haven't watched it, it's a great movie. I highly recommend it. And so we're going to talk about the Zane between neurons. So remember we already talked about action potential. We talk about neurons with and without myelin sheaths. And now we're going to talk about how do neurons communicate with each other. And this process is actually called synaptic transmission. So now we have two neurons here. As you can see, we have the brain synaptic neuron. You can simply understand it as the sending cell, the neuron sending the action potential to the next neuron. And if you remember our previous videos, all of our biological system is electrical based. However, there is some chemistry sneaking in between. I will talk about why is that later. And now we have another neuron called postsynaptic, or the receiving cell, or the receiving neuron. And then this little black square here is the synapse. So we're traveling, or the information or communication is traveling from electrical to chemical to electrical again. By the way, is it just me, or is this neuron synaptic communication image kind of similar to the creation of man by Michelangelo in the Sistine Chapel ceiling? Anyways, we're gonna zoom in on this little square here, and here's a little bit of warning. The following content may trigger trypophobia. If you have trypophobia, proceed with caution. Okay, now here we have the presynaptic neuron and the postsynaptic neuron. Or we can say this is the axon terminal of the presynaptic neuron, and this is the dendrite of the postsynaptic neuron. And in between is what we call the synaptic cleft. It's usually around 20 to 40 nanometers wide. Let's start from action potential, right? So we have action potential, and we remember our old friends here. We have sodium, the sodium channel. We have potassium, the potassium channel. We have some nuclears joining in. We have the calcium and the calcium channel. And there are some other things that we need to address, but let's go from left to right. So we have something called the vesicles. The vesicle is basically a closed membrane sac, which is a very fancy way to say it is a rounded container that packages all of the neurotransmitters inside. And so this is the first function of vesicles, is storage. It stores neurotransmitter, or it packages neurotransmitter in a bag. So if you remember our previous videos, when we have the action potential traveling in like a wave, the inside becomes increasingly positive because the gate is for sodium is open, and sodiums are traveling in, and then this area would become increasingly positive, right? Increasingly positive. And it will basically push the electric wave towards these vesicles. And what happens next is that with all of the positive charges, it will trigger another gate to open, which is the calcium gate. And the calcium would float in and bind, or we say fuse, with these vesicles here, right? And just imagine you have a lot of weight on a balloon. The balloon would fall, right? It will, because of gravity. And when the calcium binds with the vesicles, it will eventually push the vesicles as a whole to bind or to fuse with the membrane of the neuron. So it's this something like this. And what will happen is, like, with the fusing of the membrane of the free synaptic neuron, the neurotransmitters will be released, right? They will be floating in the synaptic cleft. And then this process is called exocytosis, which is a second function of the vesicles. Exocytosis. It stores neurotransmitters. It releases the neurotransmitters. And now, with all of the neurotransmitters now being released to the cleft, what happens next is that some of them, not all of them, some of them would be binding to the ligand-gated channels. So the ligand-gated channel is where the chemical or the chemistry components come from. Not everything can be bound into the ligand-gated channels. The ligand-gated channels are very picky. Some ions, like neurotransmitters, sodiums, and chlorides, can be allowed in or can be bonded into ligand-gated channels, but some cannot. Just imagine, like, there's a super popular concert somewhere, and some people's got VIP tickets, and some people are waiting around to see if they can, sneak in or, get a last-minute sale. It is how selective the ligand-gated channels are. And let's say we have our neurotransmitters bonded with the ligand-gated channel. What happens next is that the sodiums would be floating in because the channel is now open, right? And also the sodiums here, we're traveling in. Now, what happens when the sodiums with positive charges traveling into the postsynaptic neuron is that the inside would become increasingly positive, and so positive that hopefully it will cross the threshold. What's the number of the threshold? If your answer is minus 55, the answer is correct. And it will trigger another action potential, another series of waves of electrical charges to move forward, to fire. Now, not all of the neurotransmitters will be bonding, as I said before. Some, unfortunately, will be damaged, or some will just disappear somewhere in our system. And this process is called diffusion. It is not the central topic of this video, so you probably will see some relevant content down the line. And some will be recycled through this protein transport. And basically, it's kind of like an ex asking, do you take me back? And then the vesicle says, okay, I take you back. And it will be repackaged into the vesicles. And that is the third function of the vesicles, is recycling. So we've learned the process of how then presynaptic neurons communicate to the postsynaptic neuron, or how neurons communicate with each other. And this whole process is called synaptic transmission. And we've learned the three functions of vesicles: storage, that's one; exocytosis, that's two; recycling, that is three. And now, buckle your belt, hold on tight. We're going to dive into something a little bit deeper. So now we've had a general understanding of the communication process between neurons. Let's see a practical example. Let's talk about serotonin. And so serotonin is a neurotransmitter that helps regulate our mood, our emotional stability, our anxiety levels, our irritability, and our sleep-awake cycle. Apparently, if your serotonin level has increased, that'll also help you increase your melatonin level, which would help you with your circadian rhythm. And serotonin, the parent of the serotonin is tryptophan. And this is what the simplified structure looks like, 5-HTP, and serotonin is usually labeled as 5-HT. And tryptophan is obtained from foods such as chicken, fish, eggs, dairy, nuts, and soy products, and basically is from amino acids. And sometimes, unfortunately, if you're familiar with a thing called depression, one of the antidepressants that has been regularly prescribed is called SSRI. Is selective serotonin reuptake inhibitor. When we talk about inhibitor, it is not related to excitatory or inhibitory of neurotransmission communication. We will talk about in the later video. You will know what is reuptake inhibitor very, very soon. Some common SSRIs, Prozac, Zoloft, Lexapro, citalopram, Proxicon. That's some of the named brand out there. Now, with that in mind, let's walk through what will happen if we take, or if a person with depression takes SSRI. So first, SSRI, just imagine here the neurotransmitters would be 5-HT, right? All of the processes will be the same. Action potential fires, the calcium channels open, calcium fuse with vesicles and cause the vesicles to drop down, and then the vesicles would be fused with the membranes of the presynaptic neuron. And then just imagine here we have a bunch of serotonin floating. Now, what the SSRI is doing is actually, this gate is blocked. And by the way, with the neurotransmitter being recycled back to the presynaptic neuron, this process is called reuptake. When I first thought about it, I thought, okay, even the serotonins I take is recycled. I'm very environmental friendly, but I was completely wrong, because it doesn't mean the SSRI doesn't increase the recycle of serotonin. Instead, it blocks the S. That's not an S. The serotonin transport protein, SERT, which means that more serotonin will be left in the cleft. What does this mean? Imagine, say, normally there is, say, 100 serotonins in the vesicles in total. And then when it was released, maybe 50 gets to bind to the receptors for the postsynaptic neuron. And maybe 10 just got, diffused damage somewhere, and 40 is recycled, right? With the SSRI, we blocked the recycling channel. What happens is that more serotonin would be left in the cleft. So before it was 50, now it's 90. And with 90 in the channel, it will increase the chances of more serotonin binding into the postsynaptic neuron, and hence increase the mood of the person who is taking it. Now, here is the realistic and also something sometimes I think the hard part is that when you're taking antidepressants like SSRI, it will take at least 2 weeks to see the effect of this antidepressant because it is a slow releasing signal. And it will take time to for the brain to restructure, to generate chemicals. And so it is a long process. It is a long process for the patient to, see the effect of the medication and also see the side effects of the medication. And it is a long process for the doctor to see if, the medication prescribed is, mostly beneficial or helpful for the patient. So in closing, what I want to say is, if you are someone taking antidepressants, please be patient with the process. You may need to wait for weeks before you feel better, or you feel the difference. And if, one particular type of medication doesn't work for you, you may have to try again with a different medication, and still it is a long process. And I know it is long. I know it is hard. But as a person who have tried several different types of antidepressants, let me end with this. Eventually, there is a light at the end of the tunnel, and don't give up just yet. That's it for today's video. If you like it, please give me a thumbs up. Subscribe. If you have any feedback or comment, please write to me down below. I'll see you next time.